So, good morning. Let's continue our discussion that we started yesterday about the boost converter, steady state, and CCM, continuous conduction mode. So, let's share my white screen to continue. Okay. So, yesterday we derived parameters that are related to the current through the inductor. Okay, so this is the inductor current as a behavior in CCM, which is something like this. The initial value is the same final value in a period because we are in cyclostationary condition. Then we have T on, and then the cycle starts again. We know that the average value of this current inductor is placed in the input side. It's here. Okay, so the inductor current is here. The average value of this current inductor is the DC input current. And we found that the input current is derived as I naught over 1 minus D. So you can write also in this way. I naught is V naught divided by the load. Okay. Then we derive the ripple current that we know as delta L. Delta IL is V naught E 1 minus D duty cycle divided FSL. And using these two quantities, then you can derive the maximum current, the peak value of the inductor current, and this is the average value plus F, the ripple, so is V naught over R 1 divided 1 minus D plus V naught D 1 minus V Q Fs. In the same way, we can get the minimum current, okay, is In minus delta IL divided by. So it's the same expression with a minus. Okay. So what happened now? Remember what we said about the boost converter, the buck converter. Okay. Remember that, for example, the delta L, okay, which is here, does not depend on the output load. Okay. In delta L, there is no R. While, for example, in the average value, there is the resistance, so you can have the load. So what does it mean? That you are increasing the load, the average value is decreasing, while the delta L remains always the same. So in that situation, it happens that increasing the load resistance at a certain point, situation occurs in which you have the current like this one, okay, increasing R. So that situation is known as the critical situation. Okay? It is the minimum possible current flowing through an inductor that makes possible to define the operation of the boost as in CCM. Okay? Basically, this is also called the boundary conduction mode, the critical mode. If you are increasing the load resistance R above this value, then the current goes negative. It means that you are in this continuous conduction mode. In that situation, since the inductor current goes negative, so the diode and the switch can be off for a certain interval of time during the period Ts. So that is the discrete. So the critical boundary divides the CCM and the DCM operating mode for the converter. Okay, in that situation, and in all the situations we analyze, the boundary condition is defined at the point at which the minimum current is zero. Critical or boundary. So in that specific situation, if you put zero in the expression of the I minimum current, then you can derive that V naught over R and over 1 minus D is equal to V naught D1 minus duty cycle 2 times LFS. So you can simplify this expression, and simplifying this expression, you can derive the inductance L. Inductance L is R multiplied D, then you have 1 minus D per value divided to Fs. Okay. And then we can, since this inductance holds for the critical boundary mode, you can call it inductance as critical inductance. Okay, so as we did for the buck converter, we can find the inductance L that you can choose in order to be sure that you are designing a boost in CCM or in DCM operating conduction mode. The situation for the boost is a little bit different with respect to that we found out for the buck converter, because this expression needs some analysis, some further analysis with respect to that of the buck. For example, remember what we said about the buck. Okay? In order to get CCM, then we can have L, which is higher than L critical. And so in that situation, you have to choose, for example, as, to be sure, R as the maximum load resistance you may have, and the buck, the duty cycle should be the minimum you may have. But here, for example, look at the duty cycle, okay? Which is the duty cycle to be choose in order to design L and to be sure that I'm going exactly in CCM. The function now is a little bit different because you have the multiplication of D multiplied 1 minus D square value. So in this way, as we did for the buck, we can define two dimensionless parameters that are K, 2LFS over R, and there we can define also the K critical, which is now is D 1 minus D square. Okay, this K critical is different from the K critical of the buck. Remember, in that case, the critical of the buck was 1 minus D. Okay, now the function is a little bit consider these two quantities just defined, then you can have that 1 is equal to K critical divided K. Okay? This is the same expression that I defined before. Now let's plot the function K critical. Okay, let's plot this function. Versus the duty cycle. So the duty cycle ranges from 0 to 1. The K critical is 0 for D0 and is 0 for D1. In particular, you can have something like this. So the derivative of this function at 0 is not null, while the derivative of this function here is null. This function has a maximum. Okay, then you can find the maximum simply by defining K critical and take the derivative versus D, and so you can get the D, for which you can have the maximum K critical is 1/3. So for D, which is equal to 1/3, you can get the maximum, and the maximum is something that okay, you put 1/3, 1 minus 1/3 square, this is K critical maximum, then you can get exactly 4 divided. So this is the expression, and then in order to understand which kind of operating mode we have to operate, okay, we are operating, then you have to compare K critical with respect to K. So if K, for example, is here, K, let me call this K1, QLFSR. As you can see here, there is a region in which K is less than K critical, and so if you are in the situation in which K is less than K critical, you are in the DCM operating mode, because as you can see here, in order to be in DCM, K should be larger than K critical, or K less than K critical, then you are in DCM. So, for example, when you are here, for all these kind of duty cycle interval, you are in DCM. Then on the external of this duty cycle interval, for example, around duty cycle 0 and around duty cycle 1, then you are in CCM, because on the external of this curve, you are operating in CCM. What happens if you want to be sure to operate your boost converter in CCM for all the possible duty cycles? Then you have to choose a K critical, which is higher than the maximum, which is 4 divided 87. If K is larger than 4 divided 27, then the CCM is obtained for all duty cycle. Okay, so what is this condition? K higher than 427 means that K is L 2LFS over R higher than 4 divided 27. It means, for example, that L is large than 4 divided 27, R divided QFS. So if you are choosing an inductor which is larger than this value, then you are sure that for the cycle range from 0 to 1, you always operate your boost in continuous reduction. What does it mean, these kind of inequalities here? Then you have to buy an inductance which is large, okay? Because you have to choose your maximum point of your critical curve, which is 4 divided 27, then you have to choose an inductance which is larger than this. But when anytime you buy something which is larger than another component, then you have to spend more money. Okay, one of the most important factors in your design, whatever electronics, is the costs. Okay, so I say that most of the time, having this kind of design is not, say, something that can be acceptable. Okay, let me be more precise. Okay, supposing, for example, and I hope that this discussion will be much clearer, that just to redraw my critical card. Okay, something like this. 0, 1, 1/3 value here, and supposing that you know that V0 over V in is your, say, conversion ratio. This conversion ratio, for example, for CCM is something like this. Okay. So typical specifications gives you the minimum and the maximum input voltage, while the output voltage is always constant. Right? It is my DC output quantity I have to get. So when you know this variation, then also you can have a measure of your duty cycle variation. Okay, so the duty cycle, okay, inverting this kind of expression in terms of D is simply PO minus V in divided V0. Okay, so if you know what is your range of variation of V in, then you can have a minimum value of the duty cycle and also the maximum value. So this kind of two parameters are known at the beginning of your design. So supposing, for example, that you are in this specific situation, your duty cycle variation ranges from this value here, this the minimum, to, I don't know, this value here, okay, which is the maximum. As you can see here, my duty cycle variation includes the point 1/3 in which my critical function has its maximum. I want to be sure, I want to design my inductance in order to be sure that for that specific duty cycle variation, in this specific range, I operate always in CCM. Okay, remember that CCM is the region that surrounds this curve, while inside this curve you are in DCM. So if you want to be sure to create a boost in CCM from the minimum to the maximum, which is your duty cycle variation, then the only thing that you can do is to accept a K value here, which is larger than the peak value. Okay, so only with K larger than 4 divided 27, here I'm assuring that the boost always operates in CCM because you are operating in this region which is external of. So in that specific situation, I have to be sure that L is designed not to be larger than 4 divided 27, the expression that R divided QFS. Okay? But what happens in the situation in which you have a different variation of the duty cycle? For example, something like this. Supposing now that the variation of your duty cycle is something like this. You have here D minimum, and here you can have the maximum. In that situation, you can now easily recognize that your duty cycle variation does not include the 1/3 point at which the critical curve has its maximum. Okay? So in order to be sure that I can operate a boost always in CCM, for example, I can, for example, accept as K value a value which is, let's say, this one. Okay? If I have K which is larger than this intersection point here, I'm pretty sure that my boost operate in CCM for all the duty cycle interval. In that situation, then I have a specific inductance. K is larger than, I don't know, K star. Okay, so that means that you have K is L Fs over K is defined as 2L Fs over R. So if K is larger than this value, where K star is the value of the critical curve for the duty cycle minimum. Okay, so in that situation, I have to be sure that this is the minimum 1 minus the minimum. Okay. So L should be larger than what? Than R, the minimum, 1 minus the minimum, square value divided to Fs. In order to be, again, sure which R I have to be considered here, the maximum possible resistance. R max, which is defined as P naught over I. Okay. So in that situation, in order to be sure to work in CCM, I have to consider the minimum duty cycle, okay? Because this minimum duty cycle assures me that, okay, for any variation of duty cycle, I'm going in CCM operating mode. Of course, if you want to operate in DCM, which is what happens inside that, what happens is that you consider a K star here, K2 stars, which is lower than this value here. Okay, so corresponds to the Dmax value. Okay, in order to be in, so this is for CCM operating mode. In order to be sure to operate the converter in VCM for all the time interval, then you have R minimum, duty cycle maximum, 1 minus duty cycle maximum square divided Q S. Okay, this is for the CCM operating mode. Okay. Even in this case, I can sure say, for example, L higher than 4 divided 26 R divided 2FS, this one. Okay. But if you choose this kind of inductance, okay, so you are looking at something that is over the peak of this curve, you are sure that you're working CCM. But the inductance you are choosing now in that specific situation is much larger than the inductance you can, say, design by using a more, say, specific expression of the inductance that takes into account the minimum duty cycle you are considering in your application. Okay, and so that means that your inductance is smaller in the value, and this means that is say less expensive. It is not larger in the package, so it brings them less parasitics, etc., etc. So, in any situation which your duty cycle variation is larger than 1/3, then you have to consider these kind of equations in order to derive the inductance. Okay, because this leads to save money to put something that is say, smaller, then you increase the density and the compactness of your application. K critical can, this value here can be also employed not just to derive L, okay, but also to derive the frequencies, switching frequency, and R if all other parameters are, say, defined. For example, if L is given, in which situation you can have just as specs L, but let's suppose that you can have L defined, and maybe you can have also the switching frequency that is chosen, as we did, for example, in the example track, say 100 kilohertz, then you can have the variation of the load for which you can are in duty cycle in CCM or DCM. But typically, what happens is that the only degree of freedom that you're choosing your design is the inductance, okay? Because R depends on, let's say, the output voltage you want to get at the output and the current variation that you can accept. And these typically are something that is defined at, say, the beginning of the design phase. Okay, so you typically arrive to design as a unique degree of freedom in this phase just in that. So this is the reason why I, let's say, use the expression of K to derive L. Okay. Are there any questions about this derivation? This discussion you can see is a little bit different with respect to, let's say, the buck converter, because in the boost, depending on the value of K, so the value of the inductance you are choosing, typically you can operate in DCM for very small duty cycle around 0, for very large duty cycle around 1, and in the beginning in CCM, and in the middle of these two intervals you are operating DCM, because the K critical function is something a bit more complicated than 1 minus the K critical of that path. So let me continue this discussion about the CCM boost operating mode. Okay. Let me add some discussion about the electrical stress voltages and current stress of the boost component. Okay, so let me redraw again the boost topology. This discussion basically is the same discussion that we already had for the back, so we can perform discussion the same way, so looking at each component one at a time, looking which is the current and the voltage across it, in order to define specific electrical limits, electrical maximum ratings of the voltage and current that component can accept. Okay, so this is the input voltage, input current, C in L. We have the switch, the diode. This is the diode current. This is the output node. This is I naught, V naught, resistance, I C naught, switch. Okay, so this is the boost. We can start from any components since we just derived the expression of the inductance. Okay, the inductance is something that we already discussed before, so we know, for example, which is the maximum value of the current. This is an important parameter. Then we know the voltage that we can accept across it, which is V in during T on, and you can have V in minus V naught during T off. Okay. So about inductance, we have more or less all the parameters already. The average value is the input current, and then you have also the ripple current. Let's continue from the left to the right of the circuit by looking at the switch current. Current through the switch is the same of the inductor current during T on. Okay, when the switch is closed, the diode is off, and so all the current IL flow through the switch. So the switch current has this waveform. This is T on. So the current ranges from I minimum, already defined, up to I maximum. Then is 0 up to this point, in which again it runs up. This is TS. In between I minimum and I maximum, we have I in, something that I can have in the inductor current. So this is the value of the input current, which is the which are the parameters that are very important for a switch. For a MOSFET, and this is a typical application for MOSFET, this switch mode power supply. Remember that the conduction losses, so the losses in power that you have when the MOSFET is on, depends on its R-on resistance. Okay, resistance due to the construction of the MOSFET that appears between its drain and the source. And so the power, it depends on this R-on resistance and the root mean square value of the switch current. Okay, so important parameters is the root mean square value of the current. How can you compute this root mean square value? As you can see, the switch current that I can have in the boost is the same switch current that you add in the back. Okay, so same of back is exactly the same current. In that case, we use an approximation. Okay, so this derivation is not exact, okay, because my derivation is to use what I call the flat top approximation. The flat top approximation is the approximation by which my current, which is a trapezoidal waveform like this, is approximated by a rectangular waveform. Okay, this rectangular waveform has this expression here. 0 when the current is 0, but when the current is not 0, it has a flat top which is equal to the mid-value between I minimum and I maximum, and which is this, let's say, mid-value between these two values, these two I minimum and maximum, is exactly I minimum. Okay? If this is my new current, then I can simply derive the root mean square value of this current, okay, applying the definition, okay, making this current to be square, average on a period, and then take the root square of what I get. In that case, we have that I switch square value, root mean square current, is equal to I in square multiplied T on divided Ts. But T on divided Ts is the duty cycle, so please multiply it. Take the root square, I can get the root mean square value, which is I in multiplied square value of the duty cycle. The current I in, okay, is the current I naught divided 1 minus d. So it is P0 over R 1 minus d. Okay? So in this way, we can have that the root mean square value is not over R 1 minus d, which is the input current, multiplied the square root of d. Okay, this is approximated, but this approximation is a very good estimation of what happened. Okay, let me discuss a little bit this equation. Okay, this approximation. We just derived this current here. Okay, the switch current here is root mean square value just like this. Okay? V naught divided by R, and then 1 minus d squared. At the end of this block of slides, I just have I reported a list of equations that are exact. Okay, so look what example happens for the CCM boost for the switch. Okay, as you can see here, the switch current is given by this expression here, okay, which is a very complicated expression. Okay, but by the way, if you look this expression, it is composed by two parts. One, which is this one, and another one, which is the other. Okay, what happens? Look at this first part is V naught divided R. Okay, supposed to be the second part to be negligible, so to be cancel out this part here. Okay, then you have the square root of 1 minus d squared, so it means that you have V naught R divided 1 minus d square root of d, which is exactly the expression I just derived. Okay, so in the flat top approximation, I'm just, let's say, eliminating this second part, this second contribution. Okay, typically this contribution is not so, say, important. Okay, so we can use this. If you want to have the exact value, you can use this kind of exact form. Okay, specifically in the exam, you can use the approximated expressions, okay, because they hold practically in most of the case. Okay, so these kind of equations that are exact expression of all what I write in a simplified form are just, say, something that you can check for your, say, to be sure, but you can use the simplified expression. Okay, simplified expression are very good estimation course, when you design a converter, say with your pencil design, so at the very beginning of the design, you need to have to manage simplified expression, not very complicated expression. Then you can simulate, convert in spice or whatever, and then you can get, so you can refine with your. So this is just for discussing with you kind of approximation. The maximum current that you can have in the switch, okay, is the same of the maximum current you can have in the inductor. So something that we already computed, okay, is I in current plus 1/2 of delta IL, the ripple current in the inductor. Another important parameter that you have to consider for any switch is which is the maximum voltage that the switch can withstand when it is open. Before, in that situation, you can easily go in breakdown of that device. So you have to choose a device which has a breakdown voltage larger than the maximum admissible voltage across it when it is open. When the switch is open, okay, here, the maximum voltage that you can have, what happens is when the switch is open, the diode is closed. So the voltage across the drain source, so this voltage here, when the diode is on, the switch is off, is exactly the output voltage, V0. Okay? V0 is larger than V in boost, so you have to consider which is the V0 voltage. Okay? This is the, and you have to be sure to choose a switch with a breakdown voltage which is larger than the V0 voltage. Pay attention that this not exist a maximum V0. V0 is V0. Okay, you have to design a boost for say I don't know 24 volt at the output, then this is pretty constant as a value. Okay, there is no as the input voltage being minimum and being maximum. V0 is V0. Look at what happens for the diode. Okay, so let me here again. So we are here now. So look at the diode. What happens to the diode? For the current flowing through the diode, we have to consider that this current is the same of the inductor current when the switch is off, because when the switch is off, the diode is on. So it's the part that we are missing here. Okay, so the diode current is null during the on. The diode is interdicted, and then it becomes something like this. The same way we did for the switch current, we know that this current here in the midway between Imax and I minimum is the input current. Okay. This duration here is the off, so it's 1 minus V multiplied PS. Okay. What are the parameters that most interest the diode? The diode has a constant voltage which is on, more or less, the voltage drop, the forward voltage drop when the diode is on, and so its production loss depends on the average current. Okay, so important average current, which is the average current, but in order to understand which is the average current, we have to evaluate which is this area, and then to average this area over a period of Ts. So the area is, we can call ID also in this way with capital I. And the area is, this is a trapezoid, so we can get the area of I max plus I minimum divided by 2 and then multiplied the TS 1 minus D divided TS. But I max plus I minimum divided by 2 is exactly the input current. This is the input current multiplied 1 minus 2. Okay? So the average value of the current flowing to the inductor is that the input current, which is a DC quantity, multiplied 1 minus 2. Remember that in a lossless converter, V in multiplied I in, so the input power, is the same of the output power, V naught multiplied I. Okay, so as I said, another time to this lecture, the ratio between I in and I naught is the same of the ratio between V in and V naught. So it is M, which is 1 over 1. We use these results several times. So in that case, I know that I in is I naught multiplied 1 over 1 minus 3 by 1. So IT average value is I naught. So the average value of this current, which is somewhere here, is I naught. But this is not surprising at all, okay? Because if you look at the circuit, is here, the current, the DC current flowing to the output capacitor C naught is null in steady state. A charge balance condition in any capacitance. So that means that no DC current can flow to C naught. All the DC current that you can have in the current through the diode ID flow interiorly to the output. So, which is the DC component of the current ID is the average value. So it's natural that the average value of the current ID is the same of I naught. So nothing surprising. I naught is also equal to V naught divided by R. Okay. So in order to get which is the maximum possible average value, you can have to consider the minimum value of the resistance, okay? V naught over R minimum. Another important parameter is the voltage, like in the transistor, is the voltage across the diode when it is off. When the diode is off, the MOSFET is on. So we have this situation. The MOSFET is on, switch on, diode is off. And then you have V naught. So, which is the voltage across the diode. The diode has this, say, direction. Okay, this is the anode, and this is the cathode. Let me consider just the voltage from the cathode to the anode. Okay, so the maximum reverse voltage. So the voltage, the diode, the reverse voltage, is the same of the output voltage. Okay. So you have to buy a diode that has a breakdown voltage which is larger than the output voltage. Another quantity that is interesting here, not for the diode, because the diode, you can buy the diode just looking at the maximum breakdown voltage and the average value of the current in order to compute the dissipation losses. It should be interesting, which is the maximum current that can flow in the diode, but we can also compute here the root mean square value of this current, because it is important to, for example, evaluate the RMS value of the current through the output capacitor. Okay, just for say computing the root mean square value of the output capacitor, I need the root mean square value of the inductor. It's not a parameter that is useful for buying the diode. I need for the computation of the output capacitor current. So let me draw this current here of the diode. Current is something like this. I can compute the root mean square value of this current, but I can approximate again this quantity by the flat top approximation. Okay. Again, I can approximate this trapezoidal current with a rectangular one. This value of the current is the input current, the value in between, the mid value between I maximum and I minimum, and the duration here is Ts1 minus T or T off. So again, in order to compute the root mean square value, I have to square this value, this rectangular waveform average over Ts period, and then to get the root square. The same way we did before is clear that ID root mean square value, let me just the square value, this current is I in 1 minus B. Okay. We can use this value for output current computation. Flat top approximation, again, we can look at the complete equations for CCM, okay, for the diode, or something that is not appear here, okay, no, it's not important. I didn't put here the expression of the root mean square value of the diode current because it's not important for choosing the diode. Okay, but again, we have something that has a part which is exactly the same we computed, and then another part which is negligible. Okay, in that expression that the correct expression, I neglect some contribution that typically most of the case is not so important. So what happens for the input capacitance? What happens for the input capacitance? Again, charge, balance, properties of capacitance. No DC current can flow through the capacitance in steady state condition, like the condition that we are analyzing now. So what that means that all the current in this input capacitance is an IC current, no DC component. Okay, no, the average value of the current flowing to in is null. So that means that this input capacitance current is simply the current through the inductance, okay, rescaled by say subtracting to it the average value of the inductor current. Okay, so this is the inductor current, okay, IL with the average value, which is the input DC current. Okay, so eliminate the DC input current, the average value, and then you can get this totally AC contribution. This current here is the input capacitance current. Okay, so if you get this input capacitance current plus the DC in current here, you can get the inductance current. So nothing surprising. We did this kind of computation, this kind of reasoning also for the buck. Now what happens that the root mean square value of this current is can be computed, let's say, exactly, and we did this kind of computation for the buck. Okay, and look at what happens that now the root mean square value depends on the ripple current, which is delta L, and this delta L divided root mean square value of 12, then gives you that root mean square value. This is exactly what we did for the buck. But pay attention, we did this kind of reasoning in the buck for the output capacitor. Now, this happens for the input capacitance. It's the presence of the inductor L, in the input side of the boost that take the current absorbed, thrown from the input port to be, let's say, smooth. There is no pulsed current absorbed from the input side. It's just something very smooth, okay? Almost constant current with a small ripple on it. And so the input capacitance here plays the same roles that, in this sense, in the back, it is played by the output capacitor. Okay? So the input capacitance is not stressed due to the fact that the inductance L in the input side make the current flowing to the input side not a pulsed current. It's a smooth current that induces very low electrical stresses on the input capacitor. Okay? So remember that this in the buck converter occurs just for the C0 capacitance. Okay? So now the roles are, say, reversed. We previously said that the switch current is the same in the boost that you can have in the buck, but also the direct current you can have in the boost is the same current that you can have in the buck. So for the direct and the switch, the current is the same. Of course, the average value will be different, okay? But the waveform are the same. For the input and output capacitor, the situation is reversed. Less stress for the input capacitor due to the presence of the inductance. In the buck, the inductance was placed at the output side, here, in place of the diode. And so, is the output that is not so stressed because the current flowing to the output is, say, a smooth current due to the presence of the inductance. Okay? That's why you maintains to hold a very flat current flow through. By the way, input capacitance, in order to be buying capacitance, have to be also chosen with respect to the maximum working voltage. So, which is the maximum voltage that these capacitance have to, say, withstand? For the input capacitance is the maximum input voltage. Okay? So remember that this is so when you want to buy a capacitance, you have to say the value, and you have to say also the maximum voltage that you can expect to withstand during normal operation. What happens to the output capacitor? The output capacitor current is in the same way, applying the same reasoning now, we understand that is a capacitor that have to withstand large electrical stress due to the fact that here we have a diode. Okay? And the diode induces a current which is a pulsed current. Okay? There is an interval which is zero and an interval which is not zero. Okay? It is not flat, smooth like that. So output capacitor has a big stress. Let me share the whiteboard. Just to describe this situation. Okay? This is the inductor current. Okay? As you can see, is a pulse current. Let me just draw the output side of the converter, in which you have the output capacitance, C0, I C0, this is ID, and this is I0, which is constant. This is the node that I call out. At the node out, we have DC current. We have a diode current which has AC plus DC. And then I have I0, which is only AC. So remember that in these situations, especially like this, we can apply just the quadratic Kirchhoff current law. The quadratic Kirchhoff current law says that the root mean square value of a current having AC plus DC components is simply the summation of the root mean square value squared of the current having just the AC part plus the square value of the DC current. So in that case, we can evaluate that I do not RMS value square is equal to ID root mean square value square minus I0. Now it is clear why we computed here the root mean square value of the diode current, because it should form in this equation. So I can put here I in 1 minus 1b minus I. Sorry, since this is not square, okay? This is just so I have to put square here, and then I can eliminate. Okay. So now we know that I in is given by I naught over 1 minus b. So I can say that I in is I naught square 1 minus b square multiply 1 minus b minus I naught square. This can be simplified in this way. So what I can get is I naught per value and multiply b over 1 minus. Okay, and so I see not root mean square value is I naught b over 1 minus b. Of course, this is just a simplified form because I employed as a root mean square value of the diode current something that I derived in a simplified form with the flat top approximation. This is not like the formula. I naught can be also derived as v naught over r b 1 minus b. Okay, and this is the expression for the IC. And the IC not current as this waveform is the diode waveform less its average value. Okay, so this area here should be the same in this one. Okay. Okay, questions? Now I think that IC not expression for the root mean square value is present here. Exactly, now it's here. As you can see, the expression now, the exact expression is a little bit more complicated, but just if you look at this part here, this is exactly what we derived. Okay, so it means that I'm neglecting this part here, that most of the case is not comparable to the first one. Okay, so due to the flat top approximation, I'm just taking care of one contribution of the contribution before. Okay, as I said before, in the exercise and in the examination, you just use approximated, just a first step in your design. Okay, then design can be always refined successive steps by simulation. This slide, let's say, shows you the entire set of current waveform and voltage waveforms. Okay. As you can see here, these are the classical waveform of pulse width modulated switch mode power converter, in which the currents are always linear or almost linear variation, and the voltage waveform are always rectangular. So this is what happened for CCM. I have to say that in boost converter we have a very heavy drawbacks for operating the boost in CCM, continuous reduction. The fact that if you want to close the loop in order to control by using a feedback loop, as I say, mentioned in the beginning of this course, okay, that you always need a control for your pack in order to, say, make the output voltage stable with respect to the input variation, the load variation, temperature variation, aging, etc., etc. Then you always feedback loop, closed loop control. Then in that specific situation, once you use all practical cases closed loop control, the transfer function between the output voltage and the duty cycle, which is the control variable that I use to change the output, as a 0 in the right half plane, which is not useful, that make the control very, say, complicated, and in most of the situation, the boost in the CCM mode are not employed for this reason. We will see the control of this converter in the second part of this course. So we evaluate better what happens in boost CCM, for example, and just for the anticipating what happens, that in CCM the boost is very difficult to control in closed loop because the transfer function between the output and the control variable, which is the duty cycle, has a 0 in the right. Leads to, say, instability, that the system is not stable again. So typically the boost is operated in DCM. DCM operating mode is obtained when you are increasing the loads, okay, as you can happen in the but when you're increasing the load, then you have the inductor current that digitally translates down, okay, because the ripple current is always the same, does not depend on R, but average value depends on R. So a situation happens eventually in which part of the current in the DS period try to become negative. So that means that the current should flow from the cathode to the anode in the diode. This is not possible. So what happens in that specific situation here? That a third time interval, which is called T3, sometimes you can find in book also T idle, both the diode and the switch are off. So there is a third operating region. The third one is in which the switch is on and diode is off. The second one, which is called T on, T1. The second one, T2, in which the switch is off and the diode is on. Exactly the same behavior of the CCM previously described. And then we have a third region in which both the diode and the switch are off. Okay. So what happens if you look at the voltage VL? If you want to look at voltage VL, let me share the whiteboard to analyze the boost in DCM. Okay. L switch diodes. No. Something like this. So we have a first operating region, and the L is this one, in which you have switch on and diode off. In that situation, VL is simply the same as VE. And this happens for T1 or T1 to be coherent with this. Then there is a second time interval in which the switch is off, then direct is on, and VL is V in minus V naught, which is negative because V naught is larger than V in minus V naught. This happens for the time interval T2. Then there is the third time interval in which both switches are off and the voltage across the inductor is null. This is at the end here ES. This is T3 or TI. Okay, so this is the voltage across the inductor. So let me discuss the steps that leads to the derivation of the conversion ratio M in DCM. So my goal here is to derive M DCM, which is V naught over V in, okay? Which is not 1 over 1 minus D, because now we have no more in CCM. What I can use is the volt second law in steady state inductors that states that DC voltage across inductor steady state is zero. So the two areas here are always the same in each TS period. So that means that V in multiplied T1 is equal to, or maybe you can get plus just to avoid change the sign, plus V in minus V naught multiplied T2 equal to 0. From this expression, you can say that T2 is V in over V in minus V naught multiplied T1. Let me discuss which is T1 plus T2. T1 plus T2 is not TS, because now we have the time interval T3. So T1 plus T2 from this expression is, let's say, T1 plus V in over V in minus V naught. And to get this expression, T1 multiplied V naught over V naught minus V. I hope that you can follow me, because I have the usual problem with my pen. I don't know what happens. I have sorry, but I think that this is a structural problem of my report. Okay, so then you can get this expression for T1 plus T2 that we can use later. So lossless converter. Remember that I have V in is V in multiplied V in, and this is also the same of V naught multiplied I naught. Or if you want, V naught square over R. Okay. So from this expression, I can derive, for example, I in is the average value. Okay, so I in is the average value of the inductor current. I in is V naught square over V in multiplied R. But I in, as I said, is just the average value of the inductor current. So, which is the inductor current? The inductor current in discontinuous conduction mode has this behavior. So is Ts here, T1, and then T2. The average value is something that is, say, here, and this is the input current. The average value can be computed easily by taking, let's say, just the area of this triangle and averaging it over Ts. So I in another way is, this is I max, is the area T1 plus Q, which is the base of that triangle, multiplied the 8 divided by 2, and also averaged over Ts. So we have these two expressions here, and then we just computed T1 plus T2, because this is T1 multiplied T0 over T0 minus T. Then we use these three equations to derive the result after the break. Okay, so the break lasts from now up to 10 and 8. Okay, see you later. So Canone Marco asks, can you repeat why the boost converter is more stable in DCM mode? Okay, this is just an anticipation of what we learn, let's say, in future lecture, okay? The problem is that when you want to, let's say, use closed loop, and this is happen, say, anytime you use the converter, to stabilize the output voltage versus input variation, output variation, temperature variation, etc. You have to, let's say, look at the transfer function that you can have, for example, from the duty cycle, so from the control variable and the quantity you want to control, the output voltage. So for the boost CCM, it happens that this transfer function leads to the presence of a zero in the right half plane. So a zero that has a behavior which is the same of a pole for what concerns the phase. This leads to a very small phase margin, so reduce the phase margin of your closed loop system. So the presence of a right half plane zero always leads to, let's say, increase the possibility to go into instability. It's very difficult to stabilize for that specific reason. I repeat, we will learn in future lecture. In DCM, there is no right half plane zero, leading to a more easy closed loop function to stabilize. And typically, the boost converter is are always operated in DCM. Okay, for that specific reason, okay? Because it's easy to make a stable converter. Okay, in CCM, this is quite difficult. It could be quite difficult. Presence of a right half plane zero in the loop gain, you can say, of your system. Okay. Let me share the screen to continue the discussion about the conversion ratio. Okay, we get these three expressions. There is another expression that I need, which is the Imax. The Imax is given by is the peak value of the inductor current. You know that the slope of this current is V in over L. Imax is reached after a time t1, so we can easily derive that Imax is V in over L, which is the slope multiplied t1. So now put all these information together, okay, and starting from this one, Okay? So let's say, for example, to put T1 plus T2 inside this parenthesis, Imax inside this one, and so we can derive the following expression. Let me write T1 plus T2 over Q multiplying Imax divided 1 over Ts, and this is I in, but I in is also equal to V naught square over V in multiplied R. Okay. Now I can replace T1 plus T2 with T1 V naught minus V in 1F multiplying Imax, but Imax is V in over L multiplied T1 multiplied 1 over Ts. So this is Imax. Okay, this one. This is T1 plus T2. Okay, and this is equal to V naught square divided by R. T1 over Ts. This is the definition of duty cycle. So this, let me change the color. This is the duty cycle. Sorry, T1 plus T2 is exactly. I change. So now I have V not here, then you have a square here. So I can say that you have D divided 3 times L. D, 2, and L. Then I have T1 that multiplies V in over V naught minus V in, which is equal to V naught over V in multiplied. Let me multiply by dividing Ts and multiplying by Ts. Okay, nothing changed, but now I have again another duty cycle, which is T1 over Ts. So I can say that T square QL Ts becomes 1 over Fs, and then I have V in over V naught minus V in divided V naught, okay, V naught over V in is exactly that conversion ratio I'm searching for. So M DCM divided R. Now this expression can be further manipulated. For example, if in this ratio I divided by V in, I can have D square over QLFS multiply Vn over Vn is 1, V naught over Vn is m dcm minus 1, and then I have m dcm over r. You are close to the final expression because I have to solve this expression to derive m, so I can write as a function of m, manipulating this expression, you can get m dcm squared minus m dcm minus d squared r over QLFS equal to 0. I promise that I'm going to change this. It's difficult to me continue to write. I'm going to have a big effort to write a simple question. So sorry, very sorry about that. I think this is the tool that I'm using, so the software tool. So anyway, this is the expression of m, so I have to derive m, typical second order equation, etc., etc., etc. And Cm is equal to 1 plus 1 plus q d square r over LFS. This is the only acceptable result. Okay, there is another result which is given 1 minus, but it's not acceptable because m should be larger than 1. Okay, so this is my something happens which is typical for DCM. For example, CM depends on L, depend on the switching frequency, depend on the duty cycle. This is good because the duty cycle is a control variable, so I can change the duty cycle and change the conversion ratio between the output and the input. Okay, this is good, but also depends on R. So this means that the output resistance is not null. Okay. What is the, let's say, the graphical representation of this M for, say, versus the duty cycle? Okay, in order to check this graphical representation of M, let me represent again the K critical versus D. Remember, the K critical versus D is something like this, having a maximum at D, which is 1/3, going to 0 for D0 and D1. Okay, and I said also that if you compare this with K, remember that K should be R larger than K critical to operate in CCM. So for example, here and here, and K less than K critical to operate in DCM. So for example, inside the card DCM. Okay, so you operate in CCM around 0 and around 1, and around 1/3 you are always operating in DCM. So depending on the value of K, which is QLFS over R, this is K, typically you have CCM operating modes for lower range of D, DCM around 1/3, and then increasing D you go in CCM. Okay? So let me plot M versus D. M is 1 over 1 minus T when you operate in CCM. So when K is larger than K critical. And then is 1 plus You have here R divided LFS. Remember that K is defined as Q at Fs over R. So that expression is simply K divided by R. K divided by T. So you can also write as 1 plus 4 T squared over K. When you operate in DCM, K less than 50. So which is the expression of M versus D? For D, which is equal to 0, both the expression give us 1. Okay? Then the card is something like this. Supposing that you have, I don't know, K, this K here, K star. For that specific K, you are in CCM up to this point, up to this duty cycle 1. And are in DCM for D1 to D2. And then for the cycle larger than D2, you are again in CCM. Okay, so it means that for D from 0 to D1, you are in CCM, and in CCM you have 1 minus 1 divided 1 minus 2. So the typical part that we have in CCM, something like this. Then for D1 up to D2, you are in DCM here. And so it happens that you have this expression here. Anytime for d squared over k is well less than 1, sorry, it's well lower, so it's well higher than 1, okay? When this part here is lower than 1, then you can approximate m in this way, 1 plus 2d divided square k over 2. And as you can see here, this expression is linear in the duty cycle t. Okay? So suppose that you have this condition, then you have a linear variation. And then when you operate again CCM for C2, then you have again a variation. When you have K, which is higher than, say, 4 divided 27, so you are operating CCM, okay, all the duty cycle, then you have something that is the classical waveform. So this is for K higher than 4. And then you have all the expression. For K, which is very large, of course, it means that you are, for example, here. K, which is very small, you are here, for example, you are operating DCM most of the time. And so what happens is that you are just a linear variation like this. So the linear part increase with K, which is reducing. So something like this is much better that you can see the waveform in the slide here. Okay, this K is reducing, rising up. M is most of the time is linear when you operate DCM because there is this simplification holds. Sorry, this is the equation is not M DCM, this is just and M DCM is just this one. Okay? So this is what happens here. As you can see, operating the boost in DCM make possible to get higher value for the same duty cycle, the same input and output voltage, higher. For the same duty cycle, you can get higher output voltage because it's higher the value. Expected that. This always event is always happen. We can repeat now the same consideration about the DCM we already have for the when you are in TCM, okay, and you want to get the same input voltage, the same output voltage, the same average output current, then the voltage and current stresses about the component are typically higher. So in TCM, the acceptance for the current stresses. Okay? The current ripple is large in DCM to expect that you can have in CCM if you have the same average output current and you have the same input voltage. Okay? So if you are using a converter operating in DCM, okay, for a certain specific level of the output current, okay, you get higher electrical stress. The peak-to-peak current, the reluctant square current are larger. So then means that you have to buy specific components that withstand larger value, reluctant square value, peak value. Typically these are more expensive, that are bigger, etc. If you increase the output power, if you want to get to the load, so if you are increasing the output average current, I naught, that means that electrical stress is even larger. So you can operate your converter in the DCM operating mode for a given output current, but be sure that your output power should be not so large, because increasing the output powers, increasing the average output current brings to ever larger and further electrical stress. So this is not acceptable most of the time. For the specific case of the boost, you are most of the time you have operate the boost in DCM because you can stabilize the closed loop in an easy way with respect to CCM, I mentioned before. So since you must operate DCM most of the time you have to operate the boost in DCM most of the time, and this situation leads to very large electrical stress, you cannot use the boost DCM for very large output power provided to the load. So this discussion just to give you some hints that you can operate the boost DCM. You have to operate boost DCM, but this circuit is not suitable for providing very large output power. So for application which the output power is not so huge to provide large electrical stress, that means shorten the life of your components, very expensive components, etc. Boost DCM is operated just for low power rating of the output. Typically, in some application, it must be useful to use back and then some means to increase the output voltage, for example, by a transformer. In that situation, you can have, say, okay, you have to buy a transformer that can be expensive, but the electrical stress is reduced, and sometimes the solution, say, is in place of a boost DCM. So boost DCM, because you have to use this for stability problem, but the output should not be so large. Classical parameters of the boost DCM, the audio susceptibility, so the variation of the output for small variation of the input is always M in any converters. For CCM was 1 over 1 minus T, now is a much complicated expression, which is this one. Small signal output resistance, so the small variation of the output with respect to the small variation of the output current now is not zero. It was always zero in CCM for any converters, now it's not zero. If you want to compute it, then you have to describe V0 in this way. Okay, V0 is M, which is the conversion ratio, is V0 over V in. And R is V0 over I0. Okay, so if you use this condition, so V0 is equal to V in, so M, and you put in place of R V0 over I0, then you can derive this expression V0 versus I0, then you can find the output. You can see that it's not zero. Okay, it depends on the duty cycle, depends on the inductance, depends on the field. So in that situation, the boost PCM has a worse regulation with respect to what we can obtain in CCM. CCM, it appears a null small signal optical resistance, and we have some optical. The gain is delta V naught over delta T, so the variation of the output for the variation of the duty cycle, the control quantity. Again, delta V naught can be expressed by V in multiplied the equation of the conversion ratio. A very useful approximation, that is the same approximation that I put here for making linear variation, describing the variation of the M in DCM as a linear. So considering, let's say, this part higher than 1, okay, so I can neglect 1 in this ratio here, in this square root, and then I can neglect 1 in this square root here, so I can see that now you can extract from the root square, and then you can have a very simple computation. Again, more or less approximated, nearly V in over V expression. So the duty cycle increases as V in, a larger V in leads to increase in this gain. Some very few words about the electrical stress of components. Let's start with, for example, the switch. The switch current corresponds to the switch, the same current going to the inductor when the switch is on. So if you have here in this slide the inductor current for DCM, which you have this idle interval here, the switch current is the same of IL during the on. Okay, so it's this triangle here. Root mean square value is important for MOSFET for computation, okay, of the conduction losses. The root mean square value of this triangle way is simply computed in the way I explained for the back. Remember, I have to square it, and then when I square it, I get a parabolic triangle. The area of a parabolic triangle is 1/3 of the rectangle that encloses the triangle. So it is 1/3 of I max square multiplied the duty cycle, D. And if you square this value, you can get this expression here. Depends on the duty cycle divided by 3 under square root. Maximum current is always the current I defined before, so P in multiplied B divided LFS, which is the average value of this current. The average value of this current is, let's say, can be computed by simply getting the area of this triangle here. The average value is I max multiply the duty cycle and if you get I think that this is an error here, sorry, but I'm just looking at this way, this equation. So it's IL average value, which is I in, not I switch. Maximum voltage is the same as before, so it's V naught, which is the high voltage in the sink, which is the voltage across the switch. This is important. Which is the voltage across the switch. Voltage across the switch is 0 when the voltage, when the switch is on, is when the switch is off, it's V naught, because the diode is on. What happens when we are in T3, T idle interval, that both switch and diode are, say, off? So the voltage at the node C here is the voltage that you can have at the input, okay, because you have the inductance, etc. People who comes in the lab last week and saw the waveform in the back in that situation that you can have at this node. Okay, here you have the diode, so the voltage across the diode is thinking like this, but in this continuous conduction mode, they see that in T3 they have no constant value here. You have something that oscillates like, let's say, this one, okay, due to the fact that, as I said in previous lecture, when both switch and diode are off, they can be replaced by parasitic capacitance across the output terminals. Okay, the diode off is a large capacitance, and the MOSFET has this output capacitance itself, and even the inductor has its capacitance across it. Okay, in real component practical circuits. This leads to a resonance circuit LC, where L is the proper L of the circuit, and C are the summation of all the parasitic capacitances you can have in the circuit. So this brings you oscillations, okay? And this is quite visible by putting a scope across this node here, and people will count in the laboratory Friday. If they didn't see yet, they can see in the next lab, which is Friday. There is another lab, and this is the continuation of the back activity. Okay, so book your seat from this Friday. I think that even next week there will be lab. As far as I know, Politecnico di Torino will continue to operate the laboratory for students. So until there is this decision about the Politecnico, the lab will be carried out. Okay, so book your seat through your student portal and follow your Friday afternoon from 2:30 p.m. There is another important thing that happens. This comes in my mind because I talked about the lab. Okay? Look at this expression here, M. What happens depends on R. What do you think could happen if R increasing, for example, you are disconnecting the load, so R becomes infinite. If R becomes infinite, M becomes infinite. So M becomes infinite means that V0 becomes infinite. So the output voltage diverges. So if you are in DCM, and you can say if you operate a buck and you are increasing the load, you go in DCM, as I said before. But in the case you are disconnecting the load in a boost, you are disconnecting the load, then the output voltage diverges. So what happens when the output voltage goes to infinite value? Typically, the boost explodes. So the boost explodes means that the output capacitor, say, explodes. The electrolytic capacitor, as I said before, has a maximum working voltage that is tailored about the voltage you can have at the output, some plus some safe margin. Okay, I don't know, 24 volt. You can have, say, 45 or 40 voltage as a maximum voltage here, but the voltage do not diverge; it goes very high level. So the electrolytic material inside the capacitors heat ups, and this, let's say, brings to the explosion of this output capacitors. This is a problem. Okay, for the boost, you cannot disconnect the load while the boost is operating because you get some. Of course, so this means that when there will be the lab about the boost, you always have to, say, maintain the connection of the load on your port. I saw in the few minutes I went into the lab Friday that some students in order to measure the output resistance when the buck is operating, disconnect the load and then put the terminal of the load to the multimeter, to the ohmmeter, in order to measure the resistance, because it's something that they have to measure according to the guideline of the laboratory. This can be done safely in the buck, but if you have the same operation in the boost, then the boost explodes. So please, even if you are in the buck, when you want to measure the output resistance, do not disconnect the load and then say measured by the ohmmeter. Put your duty cycle to 0, put your input voltage to 0, and then disconnect the load. Okay? This is the safe operation. This is the boost is very important not to disconnect the load when they are operating. Okay? Because the boost does not survive to this operation. Diode current and voltage stress. The diode has the current which is the same of the inductor current when you are doing the off, so when the MOSFET is off. And so we have this waveform here. Like here you have the average value, which is important, okay, in order to compute the conduction losses. The average value flowing to the diode is the same of the output current I0. So this is correct. So the average current is I0. The average current can be easily computed by looking at this area here. Is a triangle, Imax divided by 2 multiplied T2, okay, divided TS average. And so you get this expression here. And this expression here is I0. Remember that I0 is equal to V0 over R. Maximum current is again Imax. I can also have the computation of the root mean square current just to compute the root mean square current of the C0. The root mean square current of this waveform is again 1/3 of the rectangle that encloses the square of this parabolic arc. So Imax square divided by 3 multiply T2 divided by Ts. So in this way, T2 is not corrected, it is D2. D2 over Ts. But anyway, Imax square root of D2 over T3. D2 is defined as T2 over Ts. Since there are few errors in this slide, I put the corrected PDF version in this afternoon, okay? So I can compute the current flow into the capacitor, the root mean square current, simply by using the quadratic Kirchhoff current. You have this node here, and this node you have IT minus I0, which is give us IC0. So IC0 root mean square value here is ID root mean square value square minus I0 square value. Okay? And so you can replace here what we already derived for IDL. The procedure is always the same. So of course the parameters that I have to face are quite different, but the operations are always the same. For the C input capacitance, the same happens as before. Is the inductor current minus its average value, which is IE. So it's this totally AC current from here. How can you compute the root mean square current here? Now, quadratic Kirchhoff current law again. IC in root mean square value is IL root mean square value square minus IN square value. And IL RMS is something that I can derive by looking at it. Oh, here. So, is the root mean square value of this green curve here. Okay, you can apply the definition. You have to square this so you can get parabolic value like this. Sorry, this here. So we Imax square here, and then you have to compute this as Imax square 1/3 of this area here, which is the area of the rectangle T1 plus T2 over Ts. This is the expression. Then you can put this expression over there, and then you can compute this. Here is not totally developed. At the end of the slide, you have, say, something which is correctly given to you, computation. Try to derive, if you want, this kind of to develop till the end this equation. The procedure is always the same. Maybe the computation can be a little bit longer, okay, to derive all these parts here, but nothing too much complicated. Okay, so let's continue this discussion by having some specific consideration about the behavior of the boost in some specific conditions and situations. The first of these specific operating condition, is what happens to the boost when you have a short circuit at the output. It can happen during nominal operation that your load, for some reason, that sometimes are totally, say, not under the designer knowledge, that you can have, for example, a short circuit. Okay? The load becomes null. What happens if the load becomes null? In that situation, in practice, it happens that there is no limitation of the current that can flow. So I naught, say, becomes very large, because here there is no resistance limiting this current. So there is a large flow of current that enters the boost converter, flow to the inductor, and flow to the diode in order to, say, to have this kind of, in order to when the short circuit appears at the output. Okay, the only way to limit this resistance is the small parasitic resistance that you can have in series to the inductors, or maybe in series to the diode, or on the input side. Okay, but they are small parasitic resistance, so they do not act efficiently with cannot limit in an effective way the current flow. You can, for example, close the switch to make the situation better. No, because if you close the switch when you, say, understand that there is a short at the output, the only thing that you can have is, let's say, something that has very small resistance in place of the switch, which is closed. So the current, which is large, now flow here. And so, with the switch which is open, the current flow and diverges in this path, only limited by the small parasitics of the component. When you recognize the short at the output, maybe you want to limit this behavior by putting this transistor to be on, a current can flow here, and when the inductor is fully charged, this current diverges, because now we have a short here, input side. So there is no way in the boost converter to managing short circuits placed at the output side. Think about what happens in the same situation if you have a buck converter. And let me share the screen. What happens if you have a buck converter? Okay, in a buck converter, you have the switch which is here, then you have the diode which is here, and then that here. Okay. Then suppose that you have a short at the output port. You have a short here, and you recognize the presence of this short. Then you can open the switch, and immediately you can interrupt the current flowing from the input side to the load. a short. So because the input, the transistor is in series with it, in series with that power flow, with the current flow. So the buck converter can easily manage the short circuit at the output. In the boost converter, this does not happen simply because the switch is in parallel with the power flow. So in that situation, when you have a short at the output, okay, even you are opening or closing the switch, okay, you cannot manage this situation. So we can say that buck can manage short of the output. Boost can manage short of the output. Okay. Another specific situation that happens in the boost. Let me draw again the boost. Now we have the load R, then we have here the input voltage, this is L, D, switch, etc. So what happens at the turn on of my converter? Turn on means that the input voltage is 0 and then suddenly it becomes the nominal input voltage. Okay, 0 to the in. Since we are operating we are starting the boost converter, the output capacitor is discharged. So V C naught, which is also V naught, is null because we are at the turn on. So in that situation, since dynamically in that specific situation time which you have turn on, the output acts exactly as a short because the voltage at the output is null. So you have to charge the capacitor C naught in order to, say, increase its level up to the nominal level, the steady state value P naught. In that situation, there is again a large current flowing here in order to, let's say, charge this capacitance or to increase the output voltage. This situation leads to what is called the inrush current. This is called as inrush current. Is a very huge current that has a larger peak than the nominal input current you may have in steady state condition because you have to charge in a very few instants the output capacitors from 0 up to its nominal value. So is something that happens just in a very limited amount of time, okay? Just at the beginning of your treatment. But anyway, it can, say, induce some malfunction, it induces some electromagnetic interference problem due to this specific specifics. There is another fact that you have to consider exactly as a turn on. When you are in turn on and you have just this kind of situation just described, so you have to, say, provide charge to the C naught capacitance in order to charge it up. What happens is that the circuit that we are discussing is a circuit like this, L and C naught, okay? The flow of charge from V in say passes through L and then goes to the capacitance C naught. But this circuit is a resonant L C naught circuit, okay? So this is a resonant circuit, and if you have a step side these resonant LC circuits, you have something like this. Let me plot V C naught versus time. That the output voltage increases and reaches a value which is 2 times the input voltage. Then it oscillates. And the frequency of this oscillation is 1 over 2 times P L C naught. Okay? The average value here is V in, but it reaches 2 V in. Okay? So, what does it mean? That there is a situation in which if you design your boost for having an output voltage which is less than V in, so not the situation in which the conversion ratio is less than 2, of course, this is a problem because you're reaching output voltage that are larger than the value that you are expecting in nominal condition. There is something that can mitigate this typical description that involves the inrush current and also the effect of resonance circuits. A situation that provides a little, say feedback, okay, in this situation. I said that there is a very huge current in the turn-on, very short timing instant of your converter. Remember what happens in real practical inductors. Real practical inductor behaves like, say, inductance, just for a limited amount of current flowing through them. If you have the graph of the flux versus the current of that specific inductor, you have a curve which is something like this. So for a limited interval of current here, the ratio between the flux and the current is almost constant. So you have L. But if you're increasing the current, the inductance, the equivalent inductance, is increasing. So L is decreasing. Up to the point for very large value of the current flowing to the inductor, then it becomes, let's say, a piece of wire, short circuit. So, in that specific situation, for example, these circuits here just holds for us, not for all the timings, but just for the, say, part of this period here. For example, when the input voltage here, sorry, for when the VC not voltage reaches V in, okay, what happens? Happens that the diode here becomes reverse biased, okay, because the voltage here, V in, now becomes at the cathode higher than the voltage you can have on the anode. So the diode breaks these circuits, and so the voltage cannot have this behavior. The fact that for huge the value of current, this inductance disappear, makes possible to not have, from this point on, let's say, a behavior, let's say, oscillating behavior, because you have no more than that. Anyway, having here a piece of wire instead of L means that you have a larger inrush current. So there is always a compromise between the two situations. Of course, you may say that, okay, we have a resonator, we can have this problem in order to say that you have to manage. I don't want to get this inductance, for example, to get into saturation, so I don't want it becomes a short circuit because I want to avoid the inrush current to become higher. So I need to put a resistor to dump out this oscillation. So I can put a resistor whatever, okay? Here you can put a resistor here, you can put a resistor anywhere, but pay attention that this kind of solution brings dissipation. Also, across the resistance flow a current, and this current leads to, let's say, power dissipated, which is not provided to the output. So the efficiency of the system is usually reduced by solution that resistive solution that tries to dump out these oscillations, okay, and to eliminate also the inrush current. So what are the solutions for this kind of problems? Okay. By the way, let me again share because this is important. This happens for the boost. The boost has this problem. But what happens for the buck? If you have a buck, supposing that you are turning on your converter, okay, and so what happens? That your output voltage is 0, so the voltage across the capacitor is null, so it acts like a short circuit dynamically for that short time interval in which you have the in increasing, you have a very large current flowing to these circuits. So you have inrush current, but you have also a switch which is in series with the flow of the current. So a solution that mitigates in buck converter the problem of this inrush current is the fact that you can increase the duty cycle from 0 to the duty cycle, the working duty cycle, so the cycle you are needed, slowly at the beginning, and this makes possible to avoid the short circuit. Okay, so at the beginning you are, say, left open the switch, okay, then you close a little bit for a very short time interval during TS, and so you say have say small amount of charges flow into the capacitor. Then you can enlarge this time interval, and then you can manage the power flow, the amount of charge you are providing the capacitor without increasing the current too much. This cannot be, and this kind of operation, sorry, is called soft start. Soft start in buck converter is typically employed at turn on by increasing slowly time instant by time instant duty cycle from 0 to the working duty cycle in order to manage the inrush current. In boost converter, this not can be used because the switch is in, say, parallel to the power flow. So I cannot use the switch for, say, managing this inrush current. In the situation which I have turned on, if I close the switch, something which is worse happens because now the current flow in this way, so through the switch. And when the switch is open, flow as I explained it before. So the problem of the inrush current is an issue in boost converter. So another thing that I can state is that buck converter can manage inrush current. Boost converter cannot manage inrush current. Okay, boost cannot manage inrush current, cannot manage short circuit at the output. How can they manage this kind of inrush current problems? We have to add something else. As I said, you have to add a resistance, but resistance increases the dissipation loss and decreases efficiency. A solution that can work is the solution depicted in this slide. Look at the top circuit in the slide. You can see there is the boost converter, and then you have another branch that includes a diode, okay, the inrush diode. So this diode here is in normal operating condition always off. It's always off because normal operating condition in the boost converter V0 is larger than Vin. and if V naught is larger than V in, this diode is reverse biased, so it's an open circuit. But there is just a few instances in which this diode is on, and these instances are at the turn on. At the turn on, so when we applied V in, but V naught is 0, or say smaller than V in, this diode is on. So the current needed to charge the output capacitor can flow through this diode here, okay, instead of passing through the inductance and the diode. Okay, I have the same inrush current. The problem of the inrush current at the input side is, but this current, which is very large, do not does not flow into the inductor and into the diode. Okay, and that can bring problems. Saturation of the inductor, maybe the diode can reach for a certain time interval a very huge current flowing through it, inducing malfunction. Okay, this can save the problem. If you want to reduce the inrush current level, the peak level of the inrush current, then you can put a resistance here to this diode. In this case, this resistor only operates in the very short time interval which you have the turn on, and so disappear. So you have some dissipation which is losses, but just at the turn on. While if you put a resistor in the circuits, I don't know, in series with the inductor, in series with the diode, in parallel with the capacitance, then that resistor are always there, even in the standard nominal condition. Another solution that is typically employed is when you can manage the inrush current by putting something else at the input port of your converter. For example, a negative temperature coefficient device, okay, NTC device placed here. Then NTC device are resistor, which resistance is dependent on the temperature. Okay, when this device is heating up, so is hot, this resistance is small. When the NTC is cold, for example, when you turn on, this resistance is very large. So at the beginning, at the turn on, temperature, no current can flow in previous time intervals, so the resistance provided by NTC in series with the current is very large, limiting the inrush current. Then, passing time, okay, what happens that it heats up, and so its resistance decreases. And when resistance decreases, it means that is almost negligible to the standard operation. So it is like to have something that is there as a resistance just for the short time interval following the stop, following the turn on of the device. Then exist some other very important solutions like the active solution. Active solution means that while the MTC is something passive, also the diode is a solution which is passive. You can use, for example, a MOSFET. You can use a MOSFET which is placed in parallel with a resistance. Okay, this MOSFET here is described by this switch. This MOSFET is actively turned on and off by a control signal, okay, an external control signal. When you have turned on, in the same way you are, say, turning off this MOSFET. When you are turning off the MOSFET, so you're opening the switch, the current flowing, the inrush current, have this large inrush current that limits the amount of current. Then, when the output voltage reaches a specific value, what happens that I can close, I can put a signal to control to this MOSFET to be closed, then short circuiting this inrush current, okay? In that case, you have no dissipation, no problems about the efficiency of your system. Remember what we said about the buck converter. So before starting this slide, which is another argument, it's very important maybe that I can summarize the difference between the buck and the boost, okay? Because I have say something about this. Maybe you can beneficial to all of you to have comparison between the buck and the boost. So we're getting the buck and the boost. Buck converter. What happens to the current which is drawn from the input side? The current which is drawn from the input, since you have a MOSFET, is of impulsive type. Okay, it's a pulsed current. So that means that the input current is pulsed. This situation means two different things. The first one is that you have large electrical stress in the input, okay, capacitor. So C in is subjected to a large electrical stress. The mean square value of the input capacitor is large, and so means that you have to buy something which is larger, expensive, is bulky, is weight, etc. Is heavy. The second drawback of this condition is that you are drawing something which is pulsing, like the back input current, drawing from the input side. So you are, let's say, disturbing the input source with this kind of pulse current. In terms of the input filter, and C in, the input capacity is a part of this input filter, means that you have to design this input filter to, let's say, eliminate these pulsed currents to reach the input side. Okay. In other way, you have to buy a very large input capacity. Okay. So there is a problem due to the design of the input filter. Seeing is very electrical stress on it, in order to avoid electromagnetic problem. This does not happen in the boost because the current is which is drawn from the power supply from the source is not pulsed. Current is smooth. Okay, and the first beneficial effect of this current is that the input filter, the input capacitor, is not so stressed. So the work done by the input filter to eliminate these pulses is, let's say, easily obtained. So less electromagnetic problem at the input, which is connected to an external power source. So this is important. What happens to the output? The output is, let's say, not stressed. Okay, so output current is smooth, and so provide less electrical stress on the output capacitor CNOT. And so that means also that you have less electromagnetic compatibility problem at the output side of the buck. For the boost, the opposite happens. For the boost, output current is pulsed. Because you have the diode, and so that means that you have put a large electrical stress on the output capacitor CNOT. So that means that you can have electromagnetic compatibility problem at the output connected to the load. Okay? Buck converter can manage short circuit as well, can control short of the output of the NOT. How can control it? By simply left open the switch. Boost converter cannot control. Short of the NOT, because the switch is in parallel to the power flow. Buck converter can control inrush current. How can control inrush current? By, let's say, increasing slowly duty cycles at a soft start. Boost converter cannot control inrush current. So external measure, external components. Okay, diode, NTC, active, etc. Let me say that we have, let me continue this table on this side. The switch in the back is of the I side switch. I side means that neither the, say, the drain nor the source of the switch is connected to ground. I side switch are maybe can be difficult to operate because they need specific gate driver. They need I side gate driver. They are expensive, they are complicated, etc. Boost converter. Boost converter has the switch which is connected to the ground. One side, the source of the MOS transistor is connected to the ground. So this is the low side switch. Low side switch means that you can easily control. Why low side switch, high side switch can control. Okay, we can say that this is something, some parameters that you can use to say, compare the. Okay, so Friday morning at 10, we can conclude the boost. Okay, next week we can have the pack boost. Friday morning 10 to 11:30 a.m. we have lecture about the boost. In the afternoon, for the students that book the seats, we have the continuation, they continue the lab in which they can continue the pack exercitation. Okay. So you have questions about what I said about this lecture or something that is related to the lab, whatever, bear in mind. If you have no questions, I can stop here this discussion. Okay, thank you very much for your attention. Of course, you can contact me by email, by phone, okay? See you Friday morning at 10 with me and in the afternoon with